Okay, in this video, I would like to talk about designing a numerical groundwater model. And as you know, the main reference of this course is Mary Anderson and William Wisner's fantastic groundwater modeling book, and the pictures and figures that you'll see in next slides, many of them are from this book. And if you remember, this was a flowchart of creating a groundwater model. We spent time and talked about how we can go and identify proper questions and define and clarify the purpose of groundwater modeling. Then we talked about how you can go and collect data and create proper and reasonable conceptual model for your questions or your project. And in last sessions, we talked about the mathematics of groundwater flow, and we derived the governing equations in 3D, 2D, and 1D systems. And we solved some example problems, and also we talked a little bit about the radial problem. So in this sessions, you'll see that actually we are going to a little bit review this section as well. And in this session, technically, we are going to be much more focused on designing a groundwater model, and we'll see what in next slide in a minute. You will see what do we mean by designing groundwater model. What do we mean by designing a groundwater numerical model? Technically, we want to translate or map the conceptual model that we've made based on the data that we collected and based on the questions and purposes of the identified purposes for groundwater modeling into language which computer can understand. You know that actually computers don't have ears and eyes, so we cannot talk with them. We cannot show a map or a sketch or a conceptual model and say that we'll go and solve this problem for us. Computers only understand numbers, and they can do very basics mathematics like adding, subtracting, multiplying. So technically what we want to do here is that we want to map or turn conceptual models into a form which is readable and understandable by computers. So the key to convert the conceptual model into a readable and understandable groundwater model, numerical model, is the governing equations that we learned in previous sessions. So we learned actually different forms of governing equations in 3D, 2D, 1D, and also in the radial form. So technically we are going to use the governing equations and some other techniques that we are going to talk about next slides and next videos to digitize the conceptual model into a groundwater models. But usually, specifically during the last years, which the groundwater models have been developed significantly, usually the groundwater modelers create 3D or 2D groundwater models. Okay, so 1D models are something that sometimes we use them, and we talked about this. We should not underestimate them, specifically once we are doing analytical study, as some of the very practical questions and homework problems that actually you worked on, so they were all on 1D coordinate system, but usually 2D and 3D are the dimensions that groundwater modelers are looking at least these years. Let's talk about the area models first. So how does a two-dimensional aerial groundwater model look like? In aerial models, technically we are looking at the groundwater from top. Okay, so we are considering a plane view or perspective of a groundwater system. For example, here as you see, this is my unconfined aquifer and this is my confined system. So herein I assume that the streamlines are all parallel and I ignore the vertical component of the flow, and actually technically I depth average the system. So technically if I go and find the head at any points, so the heads at these points are all the same. So technically if you're looking at from the top, this is my x and this is my y, and technically I want to go and find the head at any x, y, and t, both in confined or unconfined system. Okay, so technically I simplify the system and ignore one dimension. So technically, for example, herein, if this is my x, if this is my y, I go and say that for example, at these x, y's, what are the heads? Again, in previous videos, we talked about the Dupuit assumptions, and we derived 2D models and talked about the specific characteristics of the 2D models, when and why we use them. And I remember we derived 2D models from 3D governing equations that we had, and we said that actually it is a reasonable assumptions in many cases, both in confined and unconfined system. For unconfined system, we said that essentially unconfined groundwater model is a 2D models, and we said that in many confined system also this is a very reasonable assumptions. The main reason was that technically the length scale of the groundwater models that actually we solve are way bigger than the depth scale of the model. So if you see here, we usually exaggerate the z-axis to clarify just only for visualization purposes. But if you scale your conceptual model correctly, you will see that actually assuming that the streamlines are almost parallel and ignoring the small vertical components, gradient components of the flow, is a very reasonable and practical assumption. And as you see here, at least we can say that in the big chunk of the aquifer or the conceptual models that we are looking at, this is a valid assumptions. Okay, we will have a little bit of problem at points closer to the boundary conditions. For example, if there is a stream here and if we want to model the streamlines exactly at points close to the boundary condition in a stream, maybe it is not a good idea to consider consider 2D models. It is better to be analyzed under 3D coordinate system because the gradients, the vertical components and vertical gradients are high, and it's better not to be ignored. But there are some research where people went and derived some threshold values to say that, for example, in which condition and for what type of problems Dupuit assumptions or 2D models are reasonable solution for our problems. Again, in previous session, we talked about the 2D form of the governing equations. We actually derived the 2D governing equations for both confined and non-confined aquifer from a 3D models. I don't want to talk about the governing equations. Again, if you have any question or if you want to study again, you can go and watch those videos that I uploaded on YouTube, and you can go and watch those videos again. But as you see, for example, here, this equation represents the head changes in x, y, and t in an unconfined aquifer. As you see, actually here I use the SY concept. But the thing that I would like to a little bit talk more about is the sign of this R. This is the sink and source. If you remember, we call this a sink and source term. Actually, this is an external recharge or discharge term. And if you look at your notes, we had this R at the left hand side. But what you need to be careful once you want to model is that if you are recharging water from outside into the aquifer, like an injection well, if you have an injection well and you push water into the aquifer, you need to use a positive sign for R. You need to assign a positive value to the R. It means that, for example, the R, you have an injection well, and the number that actually you would assign to your well is positive 500. But if you are pumping water out of the system, okay, once you pump water out of the system, you need to use a negative sign. Okay, so it is very important. So you need to use negative 500. So technically, if you miss the or you make a mistake in assigning a proper sign to your R, or to your, which is usually it is a pumping rate, if you make a mistake there, technically, instead of, for example, getting water out of the aquifer, you would actually modeling a system which you push water into the system, or vice versa. Okay, so be careful with that. This is again a 2D confined aquifer governing equations equation that we talked in previous videos in detail. And again, we have a recharge sink and source term here that actually I'm going to a little bit talk more on this sometimes confusing parameter in the next slide. So your system can be fully a confined system, or fully a confined system like this, or fully unconfined system like this, or the mixture of both confining and unconfined system. But for the confined system, for example, if you look at this case, technically we know that the upper confining aquitard can be leaking, so it would not be a fully impermeable layer like bedrock. So they are clay or clayey layers. So we know that, for example, if we have a leaky aquitard at the top, and this is our confined aquifer, and we have a shallow aquifer there. So technically, we already solved this example problem as one of our homework. So technically, if I know the head here, which is nothing but the depth of the shallow aquifer, and if I know the head here, I can go and write a Darcy's law for this part and calculate how much water is getting from the shallow aquifer into the aquifer, or the other way. Okay, so we solve this problem. So we can go and calculate R for our governing equations that we had in previous slides, and we can go and calculate the recharge. So it is simple again here. This is the formula, which is nothing but Darcy's law. This is the for example, the head. So let me draw it again here. This was my clay layer, and this is my aquifer. shallow aquifer. So I can go and compute the head at any delta t here, and if I have the head here, then for each time steps I can go and calculate the aquifer for any position or any location at any time. So that recharge would be itself a function of x, y, and t. So they may change here, space, point by point, and also they may change temporarily. This is one form of recharge for the unconfined aquifer. For confined aquifer. For unconfined aquifer, we said that we already talked in detail in previous videos. I don't want to repeat them again. But we said that technically the physicists, the soil physicists, they go and consider the surface, the ground surface, as a boundary condition, and if a recharge happens or rainfall happens here, they go and calculate how much of that water can go and how it can go and reach the groundwater table. So, but if in any way, if we go and get some information to know how much water is going and get into the aquifer, that is our R. For example, that would be the other way. So for example, if we know that the roots of the plants are distributed well into the unconfined or shallow aquifer, we know that the plants takes the water up and evaporates. Okay, so technically we can go and calculate the ET and consider ET and convert it to the R term in our models. So let me introduce two terminologies that sometimes we see in the groundwater textbooks. As you see, if this is the Darcy's law, technically this term can be sometimes in the textbooks and groundwater literature they call it a Likens term. So here it is a vertical Likens, that would be horizontal Likens, but this is a Likens term. And there's another term that I don't see much groundwater people using this concept, but anyway, if you inverse the Likens, then you can look at that physical property as the vertical resistance of the groundwater flow. So this much looks like a heat transport term, but this is the term that actually we use a lot in the groundwater literature, and it is nothing but hydraulic conductivity divided by thickness of the aquifer. Okay, now let's talk about the profile 2D groundwater models. So they are pretty much like an aerial models again, but in this system we are looking at the groundwater problems from different perspective. Now technically here we are looking at the groundwater from the sides, and herein we ignore the head changes either in X or Y direction. So technically we have the head changes in the X and Z direction. And for example here, as you see, we assume that the water flows parallelly like this, and it does not do something like this in the y-axis, or sorry, in the x-axis. Okay, so it is parallel, but it can dive in and actually it can move and do something like this in the z direction. So this is a very interesting form of groundwater models that you'll see in next slides. I will show you some very interesting and practical cases where we want to consider a profile form of a groundwater model. So this is the first example for a 2D profile groundwater models. For example, in this system, as you see, these small bars are recharged, and you see that actually they change spatially, they're not constant, and because of this spatial variation, we have some sort of regional groundwater flows, which are very important. And as you see here, technically we are interested to know what's going on in the z direction and what is going on in the x direction. So technically in this form of problem, we want to go and understand the head changes in the x, z, and t domains. And so if I want to look at this problem, so this is actually the other axis or the other face of the problem that actually we ignore. We assume that in all y directions the head is constant. Okay, so this is one form. The other interesting example is the so once we want to study the hyper interaction between the surface water and groundwater system in the hyperhake zone at points close to the streams. As you see here, for example, in this example, so we can assume that the groundwater moves or gets into or out of the aquifer parallelly like this, and we ignore this y dimension, and we focus more on what is happening in the z direction and in the x direction. Okay, so technically I can go and find how the head is distributed spatially and temporally in the x and z direction. Okay, so this is another case where we want to do a 2D profile for groundwater modeling. Saltwater intrusion is another interesting case that you can see why we simplify and use 2D models. And again, in this case, we want to know how the head is distributed in the z and x direction. Let me correct my x direction. So we usually use the sea level as the datum. So we want to know how the head changes in these points. And as you know that actually the oceans are huge. If this is my ocean, I can assume that, so I'm talking about this direction. So I can assume that the water gets into the ocean parallelly. So I can ignore what's going on in this axis and just focus on this streamline and in the z direction. Okay, so this is another form of practical 2D equations, 2D groundwater models. And the last one, for example, in so many engineering problems, for example, if we have a dam like this, we would like to know how the water goes and interacts in the z direction. For example, if this is my dam, and if the water is stored there, so this is a very classic soil mechanics problem, if you remember. So we had the streamlines like this, right? So in this case, we are much more interested to know what is going on in the x and also in the z direction. So we technically ignore this axis and we assume that everything is constant in this axis. Okay, so this is another form of 2D groundwater models. So axisymmetric profile models are a different form of groundwater models. Sometimes they can be considered as 1D, sometimes 2D. It depends on the problem that we have, but they are categorized under the radial flow problems. So as you know, the control volume of the radial system is a cylindrical control volume, which is different from the cubic Cartesian form, and that's why the governing equation looks different. But when we use radial flow, technically, if we are interested to go and analyze the streamlines at points close to the well, we usually consider a radial system or radial coordinate system. But there are some ways and tricks that you can apply and use a Cartesian system and manipulate the transmissivity and the hydraulic properties of your Cartesian cubic cells, and go and use the Cartesian system and solve for the head changes at points close to the wells. For example, this is a paper that actually, if you're interested, you can go and see how they can use a Cartesian system to solve radial problems. But the radial problems are actually very interesting, and people are working on them. And you need to be careful. I mean, once you are designing your conceptual models, pretty much you should be able to pick a proper approach to solve the problems. But for example, in this specific figure, if you have a well, and if it is, for example, screened right at the middle of the confining aquifer, you can assume that the water, the streamlines, are getting into the well in the bigger scale, into the well radially, for example, but at points in this form. But at points closer to the well, you can assume that actually your control, you see that actually the water gets into this, not even from these sides, but also from the top and bottom of that point. So you see that actually now we have the radial streamlines like this in this form. Similarly, very similarly like this. But we usually in our groundwater models, so we usually use the Cartesian systems, and at least in the biggest scale problems, for example, if this is the area of my problem, this is my x and y, and for example, from here to here is, I don't know, like in the order of, for example, 10 kilometers, this is like, I don't know, like 5 kilometers, and if I have wells, a few wells like this, then I can assume that actually, for example, if it sits in this well cell, this is in this cell, so I can assume that I have a local recharge term, and that is a specific cell which models my the impacts of pumping in that scales. But if I want to zoom in into this small area, then actually it is probably better to use a radial system, or I need to go and manipulate the properties of the systems. And technically, some people are combining these two grid forms, the Cartesian and radial form, at points close to the wall. They go and use a radial system. But as you will see in the next sessions, there are multiple well packages that actually are doing a great job on taking care of the pumping wells. So those were 2D form of the groundwater problems, and technically based on the questions that we have and the conditions we have and the assumptions, the amount of time, the amount of money, the amount of data and form of data that we have, we go and decide it is better to model a 2D groundwater system or a 3D groundwater system. But technically we can go and apply and use the solver to solve the 3D groundwater equations like this that we already talked about in previous models, and go and solve for the head changes in x, y, z, and t. Okay, so technically in our previous in the 2D system, so if this is my system and this, if it was my confining layer, so I assumed that my cells, numerical cells, are like this. So these were my numerical cells because I just assigned one head for the entire depth of the aquifer. Okay, so this is its concept that I believe that actually now you have much better understanding of the system. So, but in the 2D systems that actually you saw like that, you could go and assign. So let me draw it. Draw a plan view. Now I'm looking at the problem, a 2D problem from top. And if these were my space discretization, my cells, I could go and assign different k values for this cell, and different k value for this cell, different k value for this cell, and this way I take care of the heterogeneity of the system. But in the z direction, I cannot do anything, right? So technically, I can define the kx, ky for each cell, and I cannot and I don't assume anything for the z direction because I don't assume any flow in that direction, right? Similarly, in the 3D system, I can go and assign not also in the x and y direction and y, but even in the z direction, I can go and assign different hydraulic properties for each cell, which changes in z, x, and y domain. So those properties would be k, I don't know, even the transmissivity of lichens, or so you see that actually these advanced softwares allow us to use cells with different sizes, or storativity, or recharge. So I can play with these and actually apply the heterogeneity in my systems. Okay, after thinking about the dimensions we require for properly modeling the groundwater systems in our problem, we need to go and think about the types and form of the boundaries that we have. So you know that actually the goal is that I have a conceptual model and I want to digitize it. Excuse me. And I want to digitize it into a groundwater model. Okay, so first I need to think about, do I need a 3D model, 2D model, 1D model? Do I need a Cartesian? Do I need a radial system? So these are the things that actually we talked about in the previous slides. Now you should have a good idea how you can go and decide based on the problems that you have, decide what types of model you need to have. For example, if you want to consider a heterogeneity in the z direction, you have to have a 3D model if it is important. If, for example, I don't know, the length of scale versus thickness of aquifer is not too high, or for example, if you want to model a system, what happens into close to the streamline, maybe it is not a good idea to use a 2D and it is better to have a 3D. So we talked about so many things in previous slides which are important and would impact our final decision dimension-wise. But the other things that after figuring out the dimension of your model, you need to think about the boundaries. And there are two types of boundaries that we can define. The first boundary is the physical boundary, so how big our model is. And we already talked about this, and we said that, for example, if you have a well-filled, the city may define a well-filled in a beautiful square block like this, but hydraulically, this is not a boundary that I can work with. Okay, so we said that actually sometimes we have to extend it, sometimes we have to squeeze it. So these are the things that actually we already talked about this. But the other important things for digitizing the conceptual model into the groundwater is that we have to go and define the boundary conditions. Boundary conditions or hydraulic property of the boundary conditions in our groundwater model. So we need to go and figure out how we can digitize our conceptual model, the boundary conditions of our conceptual models, and show how the outside world is interacting with the groundwater flow within the conceptual model. So this is the definition of the hydraulic boundary condition. And that would be in all directions. For example, if this is my for example, if this is my for example 3D confined model or conceptual models, I need to think about how the upper layer, if it is not a fully impermeable layer, I need to define a recharge here, which is a boundary condition. I need to think about the boundary condition here, and also if there is another aquifer below, this is another boundary condition. And these, for what's going on in the sides, are different boundary conditions. Okay? The hydraulic boundary conditions. Technically, there are we have three major boundary conditions, and maybe it's not correct. We say that these are the hydraulic boundary conditions. So technically, we use these boundary conditions that you're going to see in this slide and in next ones. These are the boundary conditions that we use to study transport phenomena. Okay, but type 1, and they have multiple names like this, but actually I put the names that we see in the groundwater literature and journal articles. So some people call them type 1 boundary condition, some uses a specified head boundary or Dirichlet boundary conditions. Okay, and what type of boundary conditions these are? If you look at this model, and as you see that actually the system has been the space is discretized into different size cells. And here, for example, these red cells are assigned to a specified head boundary condition. It means that I know what is going on in each cell. So it means that for example, I go and assign for this cell that actually I said that whatever is happening within the system, the head in those cells are always known. For example, the head there is 10 meter. Okay, but so it doesn't mean that in all cells I need to go and use the 10 meters. So for example, at the cell beside it, the head would be, for example, 10.1 meter. Okay, but the idea is that technically I know that the head, so the head changes at that specific cell is known. But again, not necessarily, it shouldn't be a constant number. So the head at that specific cell, I would say that it is a function of time. So the head changes with time. Okay, for example, at T, for example, I can say that, for example, at T greater than equal to 0 to, for example, 10 days, the head is 10, and after 10 days, it starts to go up with, for example, this function. Okay, so it varies. It would vary even with time, but the idea here is that I know what's going on there. How? I don't care. I mean, I need to go. We're going to see in the other slides, but though the head information is known in those cells. So this form of the boundary condition, we call them specified boundary condition, that can be constant or time varying, but you need to be very, very careful, and sometimes this causes an expensive or very bad, so they may lead into very bad and nonsense results, and it is very important to think about it. I've seen that actually so many groundwater modelers, sometimes they had a problem with this, which is not good actually. It is a very small thing, but it is very, very important. Okay, you need to be careful that this form of boundary condition has an infinite capacity to supply or remove water from the model. So what does it mean? It means that let me explain it this way. For example, if you are looking at from top, so I would like to go and zoom in into, for example, here. Okay, so if I zoom in there, I will see that, so for example, there are two cells here which are connected to other cells inside. So these are my boundary conditions. So I specify head here. I said that I know how the head changes here with time. Okay, so it is independent of what is going on here, and technically it means that if there is a flux here, and even the huge flux here, the head will not change here. So technically it is like a sink. For example, if you have a Mississippi River here in this cell and it gets into this cell, it doesn't change anything there because I forced the computer not to change it. So you may have a huge flux here in either direction. Okay, for example, if you have thousands of, so if you put thousands of wells here, for example, let me use different color. So I explain it differently because it's very important. So for example, here, if I put hundreds of wells here, the system won't dry. Why? Because I forced the system to have a fixed head here, and it supplies an infinite amount of water, and always I have water because I fixed the head there. So I always fix the head there, and actually they can feed these pumping wells. Okay, which may not be a proper thought, but you need to be careful and think about these boundary conditions, specifically once you want to check the accuracy or the correctness of your model. So this is a very important note that actually I want you to think about it and always consider. Similar to the type 1 boundary condition, which was the specified head boundary condition, type 2 is a specified flow boundary condition. which is also called as Neumann boundary condition. Now, in this situation, I go and assign a specific known flux information or gradient information for each cell. Okay, so I always say that the gradient in this cell is in a specific value. It means that actually always the velocity of water at this cell is constant. So that would be constant. Technically it is known, okay, not necessarily constant. So it means that the flux at that well, similar to the specified head, would be, for example, at t less than, for example, 10 days, it is like, I don't know, 10 whatever its unit is, and at t greater than that, greater than 10 days, for example, it suddenly jumps into 20, for example. Whatever it is, whatever it's going on here, the gradient won't change in these specific boundary condition. Okay, a no flow boundary condition is one form of a specified flow boundary condition, but in this specific case we set the flux into 0. So it means that actually the water cannot get into or out of the system from that point. But the things that you need to be careful here for this boundary condition is that in this specific situation, the problems which sometimes happen is that the computer does not care about how the head changes here. So maybe I need to explain it again here, is that you need to be careful that in this form of boundary conditions, you just say that the head, the flux or the slope of the head at that cell is known. Okay, but the head can change. Okay, so these are the totally two different concepts that actually I hope that you've been thinking of and you can digest it well. So the head can change, but the gradient doesn't change. Okay, so this is a thing that you need to think about. So the problem with this boundary conditions that you need to be careful is that if you make a mistake in your model, you'll see that the head can go up that cell dramatically, but you've already assumed that the gradient has not changed. So this is something that you need to be careful and look at and make sure that actually it makes sense. Okay, for your model. So similarly, if I want to have a similar example, if I have multiple wells here, it means that actually they get water here, but in this situation, the head in these cells drops, but the gradient doesn't change. Okay, so these are the things that actually you need to gain experience on and think more about them. The last boundary condition is type 3, or head-dependent boundary, or Cauchy condition, or boundary condition, or a mixed boundary condition. So it has multiple names. And as you can guess, it is a combination of type 1 and type 2 boundary conditions. So in this specific boundary condition, I assume that I have an information of how the flux changes with the head. So it means that actually the model goes and compute for that cell how the head changes, and based on that I go and compute the flux. And this is the equation that actually we usually use. And you see that actually technically most of the times once we have a water body out of the system. For example, assume that there is a lake here, and we know that this lake gives water into my aquifer, but I'm not interested to go and solve what is going on here. So what I am interested in, what I need, is that how this lake contributes to my system. So in this situation, I go and assign a mixed boundary condition, for example, for these cells, and say that based upon the let me erase this. So based upon the heads which are calculated for these cells, okay, so I know those how the head in those cells changes, and based on the information that I have about the stage of the lake and this length and the hydraulic conductivity of this space, I can go and find how this lake contributes to my system. But it is important, actually it changes. It's a function of the head at these cells and also the head or the stage of the lake. So this is again a pretty much like a Darcy's law. And if I want to, if you look at your, so technically we solve an example problem or homework problem on this. So, and we practice this concept. So this practice is like this. So I have a lake here. So this is one container, and this is the length of what I have. This is the hydraulic conductivity of the medium, and this is my cell. This is the boundary condition that I have there. So the other boundary condition, so the other cells are here. So based on what is going on here, I go and first I go and compute the head here. So this is constant and known, this is constant and known, and I assume that I have enough information and I know that how the state changes. So based on this, I can go and calculate the amount of water which gets into the system from this phase. Okay, so it's a very interesting boundary condition, but that actually we use. So there are some specific packages that actually they use the similar concepts that we have here. So I will stop here, and actually I will continue from next sessions, but what I wanted to discuss in this video was that I wanted to know that why and where we use 2D, 1D systems. So the dimensions they were important, and also I wanted you to think about the form of the boundary condition, and we're going to practice these boundary conditions again and again and again, and we are going to repeat this, and you'll get familiar with. But I try to explain everything in a plain language, and but if you have any questions, you can send me an email, or you can go and look at the textbook. So you will see there are a lot of fantastic sources that you can go and use to learn more about these boundary conditions. But actually my goal is that I would like to explain everything in a simple and plain language. And as you see here, for example, those example and homework problems that you solve, so we are going to use the same concepts and the same everything. So knowing those mathematics will help you a lot, and now you'll see that actually if you know the concepts now, you can similarly you can easily go and learn very important tricks of groundwater modeling.